Okay, time to continue. I had to make it so that characters in my game can't hear themselves when talking, because that was an issue before. But now that I have that off, that should fix something. Yeah, okay. Okay, so I can dynamically allocate a single object. Like, what about a standard string? Or what about, I don't know how you do it for the array, but we'll end the standard, I don't know. Because isn't a standard string a standard vector of characters? So it's an array, so maybe this doesn't work. Oh, okay. So far, so good. But maybe a standard string is still just one object. It's still one class. It's not explicitly true. We're not explicitly creating an array of something. We're not dynamically allocating memory for multiple things. We're just doing it for one object. And then we assign value to it. A standard string, a pointer to a standard string called string pointer. And it is now Ethan. Hold. Oh wait, oops, sorry. That is the new standard string. And then we could say SP now holds the value Ethan, right? And then we could delete it. I could also output it. I only want to do this if SP. Okay, but also want to end the line. Excuse me. Okay, but then if we delete SP, then is it going to catch this? Oh, it didn't say anything. Interesting. Oh, we're on inline. Sorry, we're on debug. This should be reading deleted memory. Interesting. Which prints nothing. Yeah, it's using uninitialized. Okay, cool. And if we check, well, it's fine. We already know what's going to happen. The address it was holding was this, and then it became this. Okay. To dynamically allocate the non-array form of the new operator, okay? So we're putting it before the type of one object that we're creating, okay? Yep. Makes sense. Then we can assign value to where that place in memory is. Cool. Yep, we can dereference it to use it. Cool. Makes sense? Yeah, exactly. Because we're not saying give me this piece, we're saying give me a piece. Gotcha. It knows straight versus it has to find out somehow. Gotcha. Just like storing a reference. We have the value of the address, or we have the value of the reference that we have to use, but then we also have to actually go there. So one, we have the address stored in a CPU register if we're talking about passing it to a function, but then we also actually have to use the address to get there. Okay. There's lots of memory when you run an application. Oh, what happened to the? Oh, My foot must have pulled that down. Whoops. Rather, I pulled the cord with my foot on accident. GG. Which cord is it? Oh, there it is. Pop. Okay. I should probably push that over to the side if I can. Better. Okay. When you run an application, your operating system loads the application, or exe, into some piece of memory. And that is some limited piece of memory that our application has. So it's basically taking a section of our computer's memory, and it probably has different spaces that it can be used. Okay. One area contains the code. The memory contains the code. The code itself is stored as binary, conceivably, in some piece of memory. So this program is here, and this is the program, this is the code, and then this is all space that it can use, and maybe other stuff. Used for normal operations. Used for normal operations. Creating and destroying. Okay. That makes sense. So some of it is held in these cases for tracking purposes, but we'll just say the rest of it is just there. So we have the code and we have the rest of the memory. And right now we've only been making programs that are using, I guess, this extra little piece, or this 1 little megabyte that's included in here by default. But now we have all this rest that we can use by saying, hey, I'm using this piece. Uses that piece. Hey, I'm no longer using this piece. Freeze it. And really, it's like, give me a piece. Using it. Here you go. Gives it back. Okay. And if it can't, null pointer or what? Get some chill music real fast. Just to get it in the queue. Oh, I gotta finish reading before I like shit, yo. Millie? That could be good. It's mostly Millie. Good. Let's start with stuff that's new. Okay. Too loud. Basically, if there's memory left, it'll say, hey, here it is. And the point is that we're storing it. Because if we only say new int, we're getting a pointer. New is basically returning a pointer to an int piece of memory. Gotcha. It's just the raw pointer value that's being discarded. Just like if I was getting the address of an existing object. Instead, it's just an address that's vacant. Or not. It probably has a magic number there, or a garbage value there. It can return it, but it's not automatic. Unlike static automatic memory, we have to explicitly say it. We have to put it back. Quest and dispose, new and delete, allocate, deallocate, allocate free. Oh, fuck, it continues with this little piano bit. That's beautiful. God damn, Millie's amazing. For stack objects, it's done automatically. We don't have to do it. Yep. Meaning that we can just say int whatever, and we don't have to store where that is. That's just stored somewhere automatically that the compiler is doing generously, nicely. Thank you, compiler. Thank you, thank you. Allocation and deallocation. So how does it work for Unreal Engine, where we just create an integer? I mean, surely more than a megabyte's being used amongst the entire program, right? Like even though pointers are used so frequently. But maybe not though, because I mean, surely there are ways to exceed, like, to get more of the stack, to get a bigger stack. And maybe it's also the case that we're only taking up that memory in the local scope. So it's not, well, if we added a bunch of classes and added a bunch of local things inside them, then, or we'll added a bunch of things inside them, if those objects exist in the local scope, the world's scope, we'll say, they just exist, then it seems like you would exceed the stack. The allocation of the allocation for heap objects is not done automatically. Oh. So not only are we referring to the object, we're referring to where it exists in memory. Oh wait, let me check. My mic might be. Bet you I was. No, okay, we're still in recording. Good. Holy shit, the computer's actually in a really good locked-in state right now. Wow. Oh, I think that's because at my previous place I wasn't able to put my desk completely against the wall because the bottom of the wall had a big protrusion. Maybe? I swear I wasn't able to. It doesn't matter. Shut up, Ethan. Alright, let's go. Basically, we have to manually do this. Okay, makes sense. How do we refer to the objects? The memory address. So we're holding them by with pointers. The pointer contain. Yeah, we want to store it so we can actually use it. Yeah, makes sense. Cool. Okay. And basically, when we're deleting the pointer, we're saying delete the shit that the pointer is holding, or free the place that the pointer is holding. Maybe still haven't seen delete, but yeah, it is. Okay. Yep. Return the memory pointed to by the pointer. That's cool. Initializing and dynamically allocated. Okay, so we can do nested stuff. Is there a preferred method? I'm not sure. And delete so far has never meant actually destroying. It has meant, in this case, freeing memory back that was previously used, or disallowing calls to a specific function or function overload. Ideally, overload. I mean, really overload. So we can initialize the object by making basically an int temporary, right? And then initializing that and storing its value. So we don't have to say, hey, pointer points to this new int, and then initialize the pointer. We could just initialize it in the same line, which is helpful. Okay, so if we do int main, and we do a pointer to an int, and just call it IP, and it's a new int, and it's 5. And so in this case, I'm sure this is maybe unused in our case. I'm trying to tell if the feeling of my fingers is just dryness or if it's because of the paint texture, like paint that has landed on my keyboard. I'm not sure. Okay, shaking my keyboard for a sec to see if anything would come out. Guess not. All right. Okay. All right. Dynamically allocate an int initialized with 5 and store its address. That way we can do let's do pop 10. And then really what we need to get in the habit of is pop. Okay. We need to tell the C++ to free the memory for your reuse. Oh, this is good. Arpeggio. Oh, very nice. The scalar form of delete. Okay, so there are different ways of deleting. And it makes sense that you would want to delete and then also set it to be null pointer because otherwise it's not null. So finally, cases where we're taking pointers and assigning them to be different shit. Nice. This feels clair obscure. Okay. Yeah, this is pretty damn good. Turn the memory pointer to about the pointer to the operating system. Cool. And then we can set it to be null. That way we can evaluate it again and say, hey, it doesn't point to anything. Yes. Deleting a pointer that is not make. Oh, let's find out. all the strings. Wow. What if we do an address? Oops. Oh, noted. Okay, we cannot delete objects that are holding stack memory, basically, or pointers that are pointing to stack memory. Can't delete stack memory. Makes sense, yeah, which is why we have to make it null pointer. Yeah. Here comes, oh, here comes Bop. Because before we never really had a big risk of getting dangling pointers. Because I mean, we would just say we would use pointers just for passing something to a function, and in that case, the pointer just gets fucking deleted after it's used. So. Oh yeah, really always, because we would return value as a pointer, and maybe we're returning, well, not even a pointer, we're just returning a standard optional and then we're evaluating it. I never really returned pointers. Makes sense that it's deallocated in this way. So whenever we create int x, without explicitly allocating it as a new variable, or as a pointer that's holding a new integer's address, the compiler is doing the allocation and deallocation, which means that when it gets destroyed, which is only when we leave scope, in my cases, right? Or we set the pointer to be, no, not really. Yeah, okay. Makes sense. Because something is destroyed, so after the function returns, so if we're returning a pointer to something in the function, well, if it's a local object, right, that didn't exist before the function call, because then it would exist on the caller and we'd be good. because we're in the caller when we return. But instead, if it existed in the callee, the called function, when we're returning a pointer to it, oh well, then the object that gets destroyed after we return the pointer, and we don't, or well, we could use the pointer right then, I think. But after that expression, then everything gets destroyed because we fully return and we're done. And that's dangling with a stack object. But in this case, now we have dangling with heap objects, where we delete the object and then we're using it. Oh, we're using a dangling pointer, a pointer that is pointing to a memory that has been deallocated, which is why the pointer needs to be set to null pointer afterwards, so we can keep track of whether it's allocated or deallocated. Okay. Could have just initialized new int with 7, but it's okay. Delete pointer, yep, return that memory to the operating system, and then we're outputting the value that's there. Let's do referencing a dangling pointer. Yep, makes sense, because it's dangling right now because it's been deleted, so the memory's been freed, so the pointer's not pointing to anything. Well, it's pointing to memory that doesn't allocate anymore. It's pointing to memory that's deallocated. Okay. Cause undefined behavior, delete the pointer. Trying to deallocate the memory. Oh, interesting. What happens if we do it? Does VS22 handle it, or does it give an error? Do this better. I need to get better at the commenting, even if it's quick. Maybe. Excuse me. Oh! What the fuck is this? Some folk shit. Voice. There it is. How old is Millie? I want her to sing my music in the future. Oh shit. Who is the vocalist? Cassie Way? Is this her voice? Cassie Way? Come on. Fuck, it is. Nah. Are you sure? Hold. Who's the Japanese lady, yo? Lyrics. Who's the singing? Am I stupid? Who are the people? Who's the singing? Lyrics, but who sung? Oh. Yamato. What? It can't be. She's singing? She's dead or Japanese voice? Wait, who are all these people? Hold. Vocal? Wait, really? Oh, Canadian Chinese living in Japan? Bro. Oh, I guess she does just sing in English, right? Wait a minute. That's totally her voice. Holy shit, her voice is really unique. Who is Cassie Way? 32? I'll be done with my game in I mean, come on. She's not gonna be, she'll be 52 max. This voice is insane. That's not undefined behavior, buddy. It's a full-on. What was it? Is it just? Is it that we can't access? Well, I'm surprised. Is the point that it needs to access the memory in order to free it? Access error reading location this A10F, and I think that's the memory that the pointer points to after it's been deleted. Like, for example, if we delete it, I need to output it. Eight, 1, 2, 3. What is the thing here? Using uninitialized? Hold. It's fine. Oh, what am I doing? Fuck. If it's not fully commented, then it won't recognize it. Makes sense. If we do that, 810F. Interesting. Okay. So maybe 810F is the place that holds the values that we were seeing earlier. Yeah, like 81, what is it? 81 something F? So maybe that's why. So in this program, we have a pointer, to an integer. It is assigned the address of a dynamically allocated integer. That dynamically allocated integer that we point to using the pointer is initialized to value 7. We then delete it to free the dynamically allocated integer. So it doesn't, well, it's not that it doesn't exist anymore, it's that memory is no longer allocated, so we can no longer use it, kind of, right? Wait, did we get the same thing when we just used it? What happens if we just use it? Oh, it didn't. Okay, interesting. So it didn't, or well, what happens if we output it? Oops. There it is. Okay, so we get it in both cases whenever we're using memory that's already been deallocated. In that case, whenever we delete it, that value 7 is probably there unless something came and changed it. Makes sense. Could have changed, or that the value could have changed. It's also possible that that memory now could have been allocated by something else. Interesting. Yeah. Yeah. Yeah, because now the operating system's doing it. Oh, fuck. It could cause the operating system to to shut the program down. Misread that. I was reading too fast. Thought it said the operating system was shut down. I'm like, crash the computer. Deallocated memory may create multiple dangling pointers, meaning deallocated memory may cause multiple dangling pointers. Because if we have a memory that multiple things are pointing to, and then we deallocate it, we have multiple pointers that are deallocated, right? So if we have a pointer that is pointing to a pointing to a dynamically allocated integer, right? But then I have another pointer that's pointing to this pointer. So it's basically, it's copying the address the pointer is getting. So it's getting that dynamic address, in this case, the address of the dynamic memory, or dynamic integer. And then if we delete new int, if we delete the pointer, then it's deleting where that's pointing. Just like we could have done delete other pointer and it would have fucked up pointer. So it makes not only pointer dangling, but it also dangles other pointer too. And in this case, we'd want to put both to be null pointer. Yep, makes sense. Yep. Yep. Canadian Chinese, man. The Canadian ladies have the crazy awesome voices. But in that case, we still have to null the other one. Ow! Okay. When you delete the pointer, if it is not going out of scope, set it to null pointer. Yeah, makes sense. Duh. Well, yeah, I mean, we can evaluate it, right? That's the whole point. Operator new can fail, meaning that what does it get when it fails? Does it get null pointer? I'm hoping. Yeah, it does set to null pointer if it fails. Nice, good. Oh, standard no throw. What is the operator overloading happening here? Is it just because it's taking the new? Is it operating on the new, or is it operating on the new in? I don't know. All right, let's see. This is interesting, but it's not what I want to hear. Operator new can fail. Can fail in some circumstances because the operating system ran out of memory. A bad allocating exception is thrown. If it isn't properly handled, because we don't know how to do exceptions, it will crash. Oh, good. Because the bad allocate will return, which will return all the way back to main, and then the program will crash, right? Oh, standard no throw makes it not throw an exception. Okay. And it instead sets it to null point if it fails. Interesting. Hmm. Well, yeah, because that's dereferencing a null pointer. Hello. Yes. Agree. Makes sense. Seems like that's what's being done in Unreal as well. So we say a pointer to an integer, and it's initialized with a new int. And in the event that the memory couldn't be allocated, let's see. Yeah, in the event that it couldn't be allocated, it assigns null pointer, which we can then conditionally evaluate value to determine whether or not it holds null pointer. And if it doesn't, or rather if it does hold null pointer, boop, 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 we handle. Okay, makes sense. Yeah, that makes sense. Oh wait, it only fails rarely and almost never in a dev environment. It's common to forget to do this check. Really? Okay. Okay. Oops. Null pointer is a dynamic memory allocation, huh? Yeah, because we're checking to see if it. So the point is, create the pointer for if it hasn't been allocated yet, set it to null pointer, and then if it hasn't been allocated, or if it's been allocated already, then we could set it to null point. Well, we could delete it and then set it to null. Well, hold on. We create it and initialize it with null pointer, and then we can check to say, hey, if it's a null pointer, then we can allocate to it, right? We can allocate and store it, and then store the address of the allocated variable, the dynamically allocated variable, and then, or at least store the memory address. And then, well, the hard part though is knowing whether it's dynamic or not. I mean, if it's not null pointer, then it means that it has to be, well, it could have already been deleted though. Let's see. A null pointer basically says no memory has been allocated. So the point is we're checking null pointer, not checking if it's not null pointer, we're just checking if it's not, or if it's null pointer. If it's not null pointer, then we can allocate. Thus, no need for the following. If the pointer, delete it, could just hold. Oh, deleting it has no effect, so there's no issue with deleting a null pointer. Okay. Gotcha. So assuming that we know that it's dynamic, if it's not null pointer, then we can delete it. But if it's been deleted already and not set the null pointer, then basically whenever you delete, set it as a null pointer. Because if you don't, you're gonna delete and then you're gonna evaluate it, and it's not gonna be null pointer. It's gonna evaluate as true. Oh, actually, if it's been deleted though, how does it evaluate? I'm curious. Excuse me. Or what are you saying? Hold. Pointer to an int called XP. We're initializing it with a new int. I honestly don't like the conditional here. Yeah, see? So you have to set it to null pointer, otherwise you won't be able to tell if it's valid or not. Okay. Gotta go. Be back tomorrow.